Hi there, welcome to your lesson on finding the area under a curve. This takes us from differential calculus, where we are finding derivatives which represent the slope of a curve, into what's called integral calculus, a second major half of calculus where we find integrals of functions, and one of the main applications is finding the area under a curve. Let's get started. So let's begin with a velocity time graph. This graph here represents the velocity of something, an object, over a period of time. We can see time measured on the x-axis and then a velocity measured here. So you can see the object travels at a constant velocity first of 8 kilometers per hour. And it does that for 4 seconds. And then after 4 seconds, the velocity starts decreasing until it reaches a velocity of 0 at 6 seconds. So we can see this steady decline in velocity. Okay, that's what the graph shows. Now let's look at what this green square represents. So that green square is an area. And to find the area of that square, we'll do 1 times 1. But let's look at the units we have as well. This square represents 1 kilometer. And the reason for that is precisely because of the units. So let's see what happens. We have 1 hour on this axis. So to find the area of this, we'll do 1 hour times, and on this axis we have 1 kilometer per hour. So 1 hour times 1 kilometer per hour, like this. If you multiply these two things, the hours will cancel, and you'll just be left with 1 times 1 kilometer, which is 1 kilometer. So that's why that square has an area of 1 kilometer. Therefore, if we want to discuss the entire distance traveled by this object, shown by this velocity time graph, we can just find the full area under the velocity time graph. Because if we find that full area, we'll have the number of kilometers in total. This is 1 kilometer, we can find all the kilometers. So let's do that now. We can do that by adding two areas. First, the area of the large rectangle here, and you can see it shaded here, plus the area of the remaining triangle on the side here, right here. So we can find those areas geometrically, right? What's the area of this rectangle here? Well, clearly that has an area of 32. 4 times 8, 32. So that represents 32 kilometers traveled by this object. That makes sense. If this object is traveling for 4 hours and it's moving at a constant velocity of 8, then that area there must be 32, and we know it travels 32 kilometers. 4 hours times 8 kilometers per hour. Makes sense. So that's what that area represents. Now let's look at the area of this part of the triangle here, or this triangle here. Find the area of a triangle by doing base times height divided by 2. So what's the area here? Well, that triangle must have an area of half times 2 times 8, which is 8. So the total area under the entire curve is 40, representing 40 kilometers traveled by this object. So even in that simple example, we've looked at a major application of integral calculus. Even though we haven't introduced what an integral is yet, we have looked at finding the area under a curve, and that's what integration does for us. Let's keep going. So here's another problem just like that. We have another velocity time graph, and we want to find the distance traveled. This time there's no rectangle, it's just a triangle. To find the area of that triangle, we need to know the base and we need to know the height. But those numbers here are not given to us, so we have to use the equation to help us find these two numbers, so that we can have numbers that we can then use to find the area geometrically. So we need that location. That is our y-intercept. Look at this equation. How do you find the y-intercept? Or let me ask you a different question. What is the value of... Okay, so we know x has a value of 0 at that point, because we can see it's clearly right here at 0. So with 0v, we need to know the velocity at time 0. So you can put 0 into this equation here for your x value, which is actually time t. And let's do that. So we find the velocity with t being 0, solve that, and we can see it's 10. And maybe you thought, maybe I don't need to do that because we already know it's 10. If you know the equation of a line, you know that this number here represents the y-intercept. So we can already see from the equation that's going to be 10. So anyway, we just found out that coordinate is 0, 10. Now do the same to find this coordinate, but in this case, this is the x-intercept. So at this point, the y value is 0. So we know this. We need some time when y is 0. So use the equation again and find out at what time is y 0. Okay, let's check our work. So this time we're replacing the v part of the equation with 0, because y is 0, and we solve here for t. We're going to solve for the x value. Solving that, we get 2. So we know this coordinate is 2, 0. Now make sure you understand exactly what we did there. It's pretty simple, but also sometimes we struggle with the simple things like linear equations, so check your work carefully here. Now that we have those 2 points, we know how tall this triangle is and how wide it is, so we can find the area under this velocity time graph just by finding the area of that triangle. Try it now. Okay, the distance traveled by this object is the area. We talked about that. Therefore, area of a triangle, half times 2 times 10, and that gives us 10 meters. So this object has traveled for 10 meters. Alright, let's keep going. We have more like this. Here's another one. Find the area under this graph. Now it just gives you a linear equation for this portion and another linear equation, a horizontal line, y equals 3 for this portion. This is not a velocity time graph necessarily, but we are trying to find the area under the graph, just like we've been doing. So to find the area, we're just going to find the area of this triangle and the area of this rectangle. But again, we need to know what these two locations are. We know this is 5, we don't know what this is. So how do we find out this location? Because we need that in order to find out how long the base is here, and we need that value also to find out how long this base is. So notice we have 2 equations, and we want to find this location where the 2 equations meet. So how about we just set the 2 equations equal to each other? 1.5x equals 3, and then you can solve and find out what x value they meet at. Try that now. Okay, so we know that has location x and then y value 3. We're looking for this x value. Set the 2 equations equal to each other. So here's one equation, here's the other one equal to it, right? We're saying when y is 3, what is this equation going to be equal to right here? Solve that for x, and we get 2. So we have just found out the location of this coordinate is the point 2, 3. 2 on the x-axis, 3 on the y-axis. Great, now that we have that point, we can find this area and this area, and combine them to find the full area. Try it. Okay, so the area of the triangle is half times 2 times 3, because this base was 2, we just found out because this is 2, and the height of this triangle is 3, so the area of that triangle is 3. And now this rectangle, if we know that this is x value of 2, then this length is 3, and this height is 3. So the rectangle is actually a square, that's 3 by 3, and the area is 9. Our total area, therefore, is 12. Again, pause if you need to, make sure you understand the details clearly here. This brings us to a really big idea. Okay, the idea of finding the area under a curve. So far we've been working under things that are not curves. They're very angular, therefore we can use basic geometric formulas to find the area. But when we have something curved, we don't have geometric shapes that can represent that area. So we're going to have to do a kind of a interesting approach that was done through history. And the approach is this. Let's say we put a bunch of rectangles under that. Because rectangles we can easily find the area of. And if we find the area of each rectangle and then add all those up, we can say that that represents the area under the curve. However, when we have these big wide rectangles, the area is not perfect because they stick up above the curve here, they go below the curve here, so there's too much here, too little here, and we don't know how close we are to the real area. We're close but not perfect. So how do we solve that problem? Well, the answer is add more rectangles, right? Make them thinner. If you make the rectangles thinner, now there's less wastage above, less below, and you end up with a better approximation of the area under the curve when you add the area of the rectangles. You can keep that going to infinity. For example, here we have these rectangles, then more rectangles, then eventually the rectangles become so tiny you can barely see them, and therefore they're a very good approximation of the area. And that's exactly what was done in the history of calculus. There's a way to infinitely apply rectangles and find the sum of those. It's like a sum of a sequence, and that allows us to find the area under a curve. So let's look at that now. So let's say we want to find the area under the graph of f of x equals x squared plus 1. That's a parabola. And we want to find the area from x equals 0 to x equals 2. So let's say again we have our curve here. Here's a parabola x squared plus 1. And we want to find that area in green. So we draw these rectangles. And we use pretty wide ones here. So there's going to be this big gap here. But anyway, we're going to find the area of these and then see if that can represent the area under the curve. So let's find the area of rectangle 1 here. Try it now. Do you know the width and the height of that rectangle? What would be the area of that rectangle? Okay, so if we added the rectangle areas 1, 2, 3, 4, we would call this the lower area, because we are creating rectangles that are below the curve. Now, we could also have created rectangles that stick up above the curve, and in this case, we could call this the upper area, or the higher area, and it would be higher than the actual area, right? This would be less than the actual area, and this would be more than the actual area. But what would be the area of rectangle 1 this time? How would you approach that? Do we know the width? Yes, we do. It's 0.5. But do we know the height? Well, we knew in this one the height was 1, but in this case the rectangle sticks up above that. So you're like, what is that height? Well, if we can find this point on the curve, we will know the height if we can find this y value, right? So we know the x value at this point is 0.5. So how about putting that in here, in this equation? That will give us f of x, which is the y value, and then we'll know the height of the rectangle and we can find the area. So go ahead now and find the coordinates of that point and then find the area of rectangle 1. Okay, great. So now if you continue that process with the lower rectangles and the upper ones, I have created a table here to show you what the results are. So if we had only 4 rectangles like we did here, if you did the lower sum, it's 3.75. If you did the upper sum, it's 5.75. So again, notice if we use the rectangles that sit below, we'll get a lower number. And if we use the rectangles that sit above the curve, we'll get a higher number. So that tells us the area under that curve is some number between those two, right? Because this is too much, this is too little, so somewhere in between those numbers is going to be the actual area. So again, we can increase the number of rectangles. Let's say we had 10 rectangles. Notice the lower sum is now this, and the upper is this. This number has gone up, this one has gone down, because there's less wastage above and below, and these numbers are getting closer together. So again, the real area is somewhere in between those. And notice as we go up, up, up with rectangles, up to 500 rectangles, the lower sum is now this, the upper sum is now this. These numbers are now really close to each other, because when you have tiny rectangles, there won't be so much sticking above or so much left out below. That means we're getting really close to the area. It's somewhere in between those two numbers. Okay, let's keep moving ahead with that idea. So here's another curve. We don't even have the equation, but we can see all these rectangles, and it says 20. So there's 20 rectangles below, 20 rectangles sitting above like that, and again, this will give us a lower area, this will give us a higher area, and the real area will be somewhere in between. So look at here, here's the lower sum, here's the upper sum. They're pretty close, and we know the real area under the curve is somewhere in between those two. Okay, let's take it further. N equals 50. Now there's 50 rectangles below, and 50 that stick up above. Barely below, barely above. So now we must be getting really close to the real area. Notice the lower sum, the upper sum. They're getting close together, the real area is somewhere in between. Next, we're going to keep going. Now we've brought it up to 100 rectangles. Now you can barely see them below and barely see them sticking up, but you can see just barely above. The two areas are very close now. The lower area is 4.62, upper is 4.70, very close to each other. The real area is somewhere in between. Now again, looking at a table that takes us to infinity nearly, look, 10,000 rectangles, well, that's basically like going to infinity. Look at the lower area, look at the upper area. These numbers are extremely close to each other now. So that means the real area is somewhere around there, right? They're both basically the same number, just off by a few decimal places at the end. So that basically we've come to the point of saying, well, we found the real area. The real area under the curve is that number, 4.66, let's say. Okay, where does this come from? This is called a Riemann sum, named after 19th century German mathematician Bernhard Riemann, who approximated the area of a region obtained by adding up the areas of multiple simplified slices of the region. So he did the same idea, cutting up the area, adding them up. Alright, and this is what integral calculus is all about. So I will describe this here, and then we'll continue with some problems using what is called the integral. Okay, here we go. We've arrived at the integral, the heart of integral calculus. So let's say we have a function, and we want to find the area under the function or the curve from x equals a to x equals b. We can write that like this. This is called an integral. It comes from the symbol for sum, and it's the idea of taking the sum of all the little rectangles like we just saw. So we can say the sum or the integral from a to b of the function, and we put dx here, gives us the area. So when we see that integral written like that, it is read as the definite integral between x equals a and x equals b. Okay, the definite integral between x equals a and b. The a number is called the lower limit of integration, and the b number is called the upper limit of integration. So for example, we have a curve here. We want to find this area. Here's the lower limit, here's the upper limit. We would find the area by writing it like this: the definite integral from a to b, of the function, and we put dx at the end here. Okay, let's use that. So here we have this line, and we want to find this area from x equals 1 to x equals 4. It says write the definite integral. That gives you the shaded area. So what would be the definite integral for this? It would be written, first of all, and in b we're going to find the value of the definite. So first we're going to write the integral, then we're going to find the value. And the word find means show your work. So we're going to do this by doing step by step, not relying on our calculator. Okay, so here is the definite integral. We know, again, we're looking from 1 to 4, so we write from 1 to 4, those are bounds, and we put the function in here, which is negative x plus 6, and we always end it with a dx here. Okay, because that means we're finding the integral and our variable of integration is x. Okay, so let's do that. Here we notice it's a line. So under a line, when we have an area, we create a geometric shape. This shape is a trapezoid. So if we can find the area of that trapezoid, we have found the definite integral, which represents that area. So the area of a trapezoid, to remind you, looks like this. We take the two bases, and those are the two parallel sides. We add them up, we multiply by the height, and we divide all that by 2, or in other words, multiply everything by a half. So here, if you look at it, where are the bases? This purple line is not one of the bases. The two green dotted lines are the bases because those are the parallel sides. So those are your two bases. Your height would be from base to base. Okay, so find the area of this trapezoid. Okay, using this formula, the area of that trapezoid will be half, like half, and then two bases added, 2 plus 5, so this base has a length of 5, this base has a length of 2, and then times the height, which is 3 here. So our area under this curve is 10.5. In other words, that is the definite integral between 1 and 4. Great, that's how integration works. That's a basic example, but it gets you used to the mechanics and the look of this symbol. Let's try another one. So here, for the definite integral, integral negative 1 to 3 of x plus 4. Okay, state clearly the function being integrated, the lower limit, and the upper limit. So let's start with that. And at the end, we're going to find the definite integral again. So clearly the function is x plus 4. There it is. The lower limit is negative 1, and the upper is 3. Great. That's just being able to read the integral. Next, sketch the graph of the function. So we can see this is a linear function. In here, we have a linear function. You should be able to graph lines. So let's try to graph that line. So first, here's our axes. We know this line, or this linear equation, has a y-intercept of 4. So here, that point, there's y equals plus 4, x plus 4, that's our equation. This point must be 0, 4, because that's our y-intercept. Now, we want to find the between lower limit of negative 1 and 3. So why don't we put two vertical lines, one at negative 1, one at x equals 3, and that's where we're going to find this area in here. So now the next thing we need to find the area is the coordinates of these 2 points, because if we don't know those two corners, we won't know how long this is or how long these bases are, for example. So how do we find those 2 points? So let's begin with this point right here. That point we know, and here's the other one. So this point here we know will have coordinates of negative 1 and some y value. We know negative 1 because that was our boundary of integration. That's what this dotted line represents, x equals negative 1. So we have negative 1 here, but we don't know the y value. Well, we have the equation, so why don't we just put negative 1 in this equation and find out the y value? Okay, so doing that work, here's our equation. Negative 1 goes in for x, and we get a y value of 3. So that means this coordinate is negative 1, 3. Great, that will help us with finding the area. Do the same for this point. Find the coordinates of that point. Okay, that one we know is 3, 7. That means we took the x value. We know this was x equals 3. We put 3 in here and we got 7 for the y. Great, now we have all the numbers we need to find the area of this shape. And this shape again is a trapezoid once again. Find the area of that trapezoid. Here's the formula again to remind you, so go ahead and find the area of this trapezoid. Okay, so the integral, definite integral from negative 1 to 3 of this function is the area of the trapezoid, which is 20. So I hope you found the same value. Check the answers here. We know we have a base of 3 here, another base of 7, so we're adding the bases, times the height of 4, and a half applied to all of that. Great. Good job so far. Let's do a couple more. So now it says calculate the definite integral. Notice now we have the word calculate instead. In the previous problems it said find. Find always tells you we're going to have to solve it by hand. Calculate means we can rely on our calculator. And that's good because this one is not like the others. This equation x squared plus 1 is a parabola. Actually, it's the same parabola we were looking at earlier. And to find the area under a curve, we know we talked about using this technique of putting many rectangles, but we're not going to go through the process of finding many rectangles, right? We're going to see now we have this tool called integration, which apparently does that. It creates infinite rectangles and finds the sum of their areas. So let's find it. Let's use the definite integral on our calc. Okay, so let me get the calculator up here and we'll do it together. So here's the calculator. We're trying to find this definite integral. So let's put the function in first. I'm going to put y equals. I've already entered the function. Please go ahead and enter the function as well, x squared plus 1. We're going to graph it in a moment. Remember when we're graphing, we might want to reset our window. So I'm going to put zoom and number 6, zoom standard. That brings us back to the 10 by 10 by 10 window, right? The basic 10 in every direction. So there's our parabola. Great. Now we want to find the definite integral. So just like we did with derivatives, once we have the graph, we can use second calc to find an integral. Remember in the last unit we used derivatives, but now we're going to use number 7, integral. We can see here. So I'm going to press 7. Alright, it says lower limit. So it allows you to actually set the lower boundary and upper boundary. It's going to put like the lines and then create the area. So what's the lower boundary? Well, x equals 0. It already assumes 0 here. Great, enter. Upper limit. Well, we want this integral to go up to 2. So I'm going to, right now it says 0. I'm just going to type in 2 and it says x equals 2. Great, enter. And now look, it made an area for us. It showed us from x equals 0 to x equals 2 under the curve, and it even calculated the integral for us here, 4.666. That should look familiar, because when we were looking at this in our investigation earlier, that's the value we came to when we had like 10,000 rectangles. We had that area, right? So here we go. That looks good. There's another way to calculate integral I should show you. So if you don't want to graph, if you want to just go straight to the functional form, here's another way to do it. So I'm going to go to quit. I'm in my main screen. I'm going to do math button. And under the math button, if you go down the list a little bit, sorry, in the math menu, you can see number 9. It says function integral. That's the one. I'm going to press enter. And look, I can enter an integral just like I see it here. So lower boundary, 0. Upper boundary, 2. And then enter your function here, x squared plus 1. So x squared plus 1. Okay, and then don't forget to finish with dx, because that's our variable of integration. There we go. Enter, it should give us the same value. There we go, 4.66666, the same value we just saw on the graph. Perfect, now you know how to do this on your calculator. So that's the value we got. And the beautiful thing is, it matches exactly what we saw earlier. As we increased the number of rectangles under that curve, we saw that our lower sum and our upper sum became close together, and they were basically leading us to this very solution here, which is with infinite rectangles. Perfect, awesome, great connections. We've learned about integration. Let's do one more. So we have a region A enclosed between this curve and the x-axis. So let's say we have, it says write down the definite integral for this. Well, here's our definite integral. We have the function here, and we want to find the area between 2 points. We don't know what they are though, because it says the area enclosed by this curve and the x-axis. So what does that mean? It means that curve intersects the x-axis and it creates an area that's kind of caught between the x-axis and the curve, and that's what we're trying to find. So we don't know what the two boundaries are yet. We have to find them. So maybe we begin by looking at the graph. If you graph this on your calculator, you should see something like this. So go ahead and graph it on your calculator. Make sure you can create that graph, because it's important that you can do this. This too, so I'm going to clear this out. I'm going to put in that function, and it is, let's clear this one out, negative x and then times x minus 3. Okay, let me put that in, x minus 3, close the parenthesis. I'm going to graph that. It should match what we have here. Okay, there it is. There's the curve. Of course, our window again is 10 in every direction, so we can see that this is here. Okay, great. So now that we have the curve, our goal is to find these 2 points, because this question says find the area enclosed by the curve and the x-axis. So we're trying to find this area in here. And if we want that area, we should definitely know these 2 locations. We can find those easily. We know that second calc. And what are those points called? They're called the x-intercepts, or the zeros, right? So we're going to go to number 2, and we're going to find out what those points are. This first one I think is pretty clear, but I'm going to do it anyway. So here's that, enter, right bound, oop, where'd it go? Go beyond that point, enter, and then estimate guess. Okay, so I'm looking for that point. That point is clearly 0, and we can see on the graph 0, 0. So we know that's 0. That's easy. How about the other point? So we know that's 0, 0. How about this one? We can see on this scale here what it is, but make sure you try on your calculator so you can see it as well, right? If you did the second calc again, second calc, and 0, you would find out the location of that point. So go ahead and try it, and we know that point is 0, 3. So now that we have the boundaries, we can rewrite our integral showing the boundaries from 0 to 3. We want to find the area from 0 to 3 right in here. Run that integral in your calculator. So again, you can either from the graph, now you can press second calc and do the integral here, or again, if you quit the graph, you can do math and do number 9, which is the integral. Your choice, or maybe try them both to make sure you know what you're doing, see what area you get. Okay, you should have gotten an area of 4.5. So if you got that area, great job. You used either technique. Excellent. You have learned lots about integration. We'll see you in class to do further work with this topic. Great job.